Tonight, imagine the mission has already done the part everyone notices first. The rocket has left Earth. The crew has crossed deep space. The landing system has survived the fall through the Martian atmosphere. The dust has lifted just enough for the horizon to become visible again. A habitat sits on the surface. A small vehicle stands nearby, half machine and half promise. Above it all, somewhere in the thin, cold sky, Earth is only a point of blue-white light. At first, it feels as if the hardest part is over. That is the familiar picture. We talk about a Mars mission as if the main story is getting there. The countdown is on Earth. The giant launch vehicle is on Earth. The drama is the outward journey, and Mars, in that picture, is the destination, the final red dot at the end of the line. But for a crewed mission, Mars is not the end of the line. Mars is the place where the return system has to stop being an idea and start being real. That is the hidden trap inside the phrase, the trip home from Mars. It sounds simple because home is a familiar word. Home feels like the safe direction. Home feels like turning around. But in interplanetary flight, home is not behind you in any useful sense. It is another engineered sequence waiting to be executed from a planet with no launch base, no rescue fleet, no spare factory, and no easy pause button. So this is not a story about Mars being far away in the usual sense. Distance matters. The months of travel matter. The communication delay matters. But the brutal part is deeper than distance. The brutal part is dependency. A crew can land safely and still be standing at the beginning of the hardest chain. They need a way off the surface. They need the propellant for that ascent, already present, already made, or somehow preserved. They need the surface systems to keep them alive while the planets move into the right geometry. They need the ascent vehicle to ignite after waiting in dust, cold, radiation, and silence. They need to reach the correct orbit at the correct time with a vehicle that cannot be casually repaired after launch. They need to meet another vehicle or depart on a path already prepared for them. They need life support to keep working across the long coast home. And then, after all of that, they need to arrive at Earth not just near to the planet, but through a narrow set of speed, angle, heat, and recovery conditions. Nothing in that chain is science fiction. None of it is magic. Many pieces are extensions of things spaceflight already knows how to do. But the return from Mars asks them to work together at a scale, distance, and duration, where the comfort of Earth's support system has been stripped away. That is why landing is not the finish line. It is the midpoint where the mission's promises are tested. Look again at the surface. The habitat is not just a shelter. It is a waiting room inside a planetary clock. The ascent vehicle is not just a small rocket. It is the first door back to Earth. The propellant tanks are not just stored mass. They are time, power, chemistry, and confidence, compressed into one future ignition. The route home is not a mirrored arrow drawn back across the diagram. It is a chain of gates, and the crew can only pass through each one if the earlier gates have already held. That is the mental model we need for the rest of this journey. Not a heroic escape scene, not a disaster countdown, not a simple reverse trip, a quiet engineering problem made brutal by the fact that every answer has to be carried, produced, tested, protected, or trusted before the people on Mars need it most. There is a strange emotional pressure in that. From the surface, Earth looks small enough to cover with a fingertip, but the entire mission is still organized around reaching that point again. Every machine on Mars, every stored kilogram, every spare part, every orbit calculation, every calm routine inside the habitat is part of a system pointed toward that tiny light. This is where the promise of the episode begins. If you picture Mars as a destination, the mission looks like a mountain climb. Reach the summit, plant the flag, begin the descent. But if you picture the return correctly, Mars becomes something else. Becomes a place where the crew is alive, successful, and still dependent on a chain that was designed years earlier. The surface moment is not victory followed by a ride home. It is the moment when the mission quietly asks, did we build home into the plan before anyone left Earth? Because getting to Mars is distance. Getting home is dependency. And the first dependence is stranger than distance. before anyone coasts back across interplanetary space, before any capsule can meet Earth again, before the word home means anything practical, the crew has to do something no human has ever done. They have to launch a rocket from another planet without Earth underneath it. Now, let's slow the picture down and replace the simple arrow with the real shape of the problem. A casual drawing of a Mars mission usually has one line going out and one line coming back. Earth here, Mars there. A spacecraft travels across, lands, turns around, and returns. It is clean, easy to remember, and almost completely misleading. A real return is not one smooth line. It is a stack of locked steps. First, the crew has to stay alive and functional on the surface, while the return system is protected, prepared, or verified. That means the surface stay is not just exploration time. It is also return readiness time. The habitat, power system, communication system, tools, spares, suits, dust control, and health monitoring all become part of the homeward path. Then comes the surface ascent. The crew has to leave Mars itself, not just lift off for a few seconds, not just rise above a hill. The vehicle has to climb from the surface into a useful orbit. It has to do that with people inside it, with guidance working, engines working, tanks delivering propellant correctly, and the vehicle still healthy after whatever time it spent waiting on Mars. After that, there may be an orbital handoff. In many broad return concepts, the small ascent vehicle is not the same object that carries the crew all the way back to Earth. It may need to meet another craft, a departure stage, or a return vehicle in Mars orbit. That meeting is not a parking lot rendezvous. It is a precise operation around another planet, far from the immediate backup of Earth. Then the crew has to depart Mars orbit or Mars vicinity on the right interplanetary path. This is not simply pointing at Earth. Earth is moving. Mars is moving. The spacecraft has to leave at a time and direction that makes the later arrival possible without wasting impossible amounts of energy. Then comes the long transit back. The spacecraft is no longer fresh from Earth. The crew is no longer at the beginning of the mission. The systems have already been used, maintained, and stressed. The return coast is therefore not a passive waiting period. It is a months-long reliability test with people inside it. Finally, the vehicle reaches Earth. And even here, home is not automatic. A returning spacecraft must meet Earth on terms the atmosphere will allow. Too shallow and the vehicle may skip or miss the intended path. Too steep and heating and loads become more severe. Too fast, too wrong, too late, or too poorly protected. And the final step can become the one that consumes all the success before it. That is the chain: surface survival, Mars ascent, orbital connection, Mars departure, deep space return, Earth entry and recovery. Different mission architectures can arrange these pieces in different ways. Some concepts lean more heavily on equipment sent ahead. Some imagine producing propellant on Mars. Some store more resources. Some combine multiple strategies. The exact vehicle names, fuel choices, crew sizes, and surface durations can change. But the shape of the return problem remains. The crew cannot use the Earth entry system if they never leave Mars. They cannot leave Mars if the ascent vehicle is unhealthy or underfueled. They cannot rely on a surface stay if the habitat does not keep them alive long enough for the window. They cannot calmly wait for the right planetary geometry if spare parts, power, food, water, or medical margin have been treated as afterthoughts. And they cannot fix a deep dependency failure by heroic willpower at the end, because the later stages only exist if the earlier stages already worked. This is why returning from Mars is so different from returning from Earth orbit. In low Earth orbit, Earth is always underneath you. That does not make re-entry easy, but it changes the psychology of the problem. You are in Earth's neighborhood. Rescue, communication, tracking, replacement launches, ground teams, and rapid troubleshooting all exist on a scale that human spaceflight has built around for decades. Mars is not that kind of neighborhood. Mars does not sit below the spacecraft like a safety net. Mars is a separate planet moving around the sun. And once the crew is there, Earth's industrial support becomes a voice in the distance. Helpful, brilliant, essential, but not physically present. So the return chain has to be designed as if the crew will need it when no one can simply walk over and repair it. A useful way to picture it is a row of gates. The first gate is survival on the surface. The second is getting into the ascent vehicle and leaving Mars. The third is reaching the right orbital target. The fourth is connecting with the return capability. The fifth is departing Mars at the right time. The sixth is keeping the crew and spacecraft functioning across deep space. The seventh is meeting Earth's atmosphere correctly. Each gate can be shown as a clean symbol on a diagram. But in reality, each gate is made of thousands of smaller agreements between physics and hardware. A seal holds. A valve opens. A computer understands its state. A battery has capacity. A solar array produces power, or another power source continues to deliver. A tank has enough usable propellant. A crew procedure is clear. A navigation solution is accurate enough. A heat shield is ready for a final environment it cannot negotiate with. That is why the return cannot be treated like an epilogue. It is tempting to say, get them there first, then worry about getting them back. But a Mars mission does not allow that sequence. The return is not a later chapter that can be solved after the landing. It has to be embedded into every earlier chapter. The mass launched from Earth depends on it. The cargo sent ahead depends on it. The surface layout depends on it. The science plan depends on it. The crew schedule depends on it. Even the amount of time astronauts can spend exploring depends on the quiet requirements of the path home. And this is where the word brutal becomes precise. It does not mean hopeless. It does not mean dramatic failure is waiting at every second. It means the problem is unforgiving because it is chained. A late success cannot easily erase an early missing link. The trip home is not a path. It is a sequence of gates. One more detail matters in this map. The gates are not equal in emotional visibility. A rocket plume is easy to understand. A docking target is easy to draw. A capsule hitting the atmosphere is easy to dramatize. But some of the most important gates are quiet. A battery remaining healthy, a software mode being understood, a valve still being within tolerance, a crew procedure still matching the real configuration of the vehicle. The return chain is therefore partly visible machinery and partly invisible readiness. A good mission has to respect both, and the first gate that truly feels like leaving Mars is the most physically direct one. A rocket has to rise from the surface, carrying human beings away from a planet where Earth's launch infrastructure does not exist. Here is the first clear proof that the trip home is not the outbound mission in reverse. On Earth, launching a rocket is already a huge act of coordination. But when we watch Earth launches, we often forget how much of the launch is not the rocket. There is a launch pad. There are roads, cranes, tanks, towers, lightning systems, fueling systems, cooling systems, inspection teams, clean rooms, range safety networks, radars, weather monitoring, emergency crews, and a giant human and industrial ecosystem surrounding the vehicle. A rocket may look alone at the moment of liftoff, but it is not alone. It is standing on a civilization that prepared the ground beneath it. On Mars, the ascent vehicle cannot count on that world. The gravity is weaker than Earth's, which helps. The atmosphere is much thinner, which changes some aerodynamic and heating problems. A Mars ascent rocket does not have to fight the same exact environment as a rocket climbing from Earth, but this is where the false comfort begins. Easier gravity does not mean easy launch. It means one part of the equation is less severe while many other parts become harsher. A Mars ascent vehicle has to be delivered or assembled, kept healthy, protected from dust and thermal cycling, monitored with limited direct intervention, and trusted to perform at the one moment when failure would cut the crew off from every later return asset. It may have waited for months or years before humans climb inside. It may have endured cold nights, dusty surfaces, mechanical aging, and the slow accumulation of small uncertainties that Earth launch teams normally fight with constant access. On Earth, if a launch vehicle shows a suspicious reading, teams can roll back, inspect, replace, test, delay, and try again. On Mars, delay is not just a calendar inconvenience. Delay may collide with the planetary window. Replacement parts are not coming next week. The repair crew is also the flight crew, and every repair consumes time, tools, energy, and human attention inside a mission that is already carrying limited margin. So the ascent vehicle is not just a small rocket. It is a machine that has to wait in an alien environment and then become perfect enough at the moment of use. That waiting is part of the brutality. Imagine leaving a complex aircraft in a desert, in cold, dust, and radiation, with no hangar, no factory line, no full ground crew, and then expecting it to start when the journey home depends on it. The analogy is imperfect, but it captures the emotional shape. The ascent vehicle is not merely designed to fly. It is designed to remain trustworthy while it is not flying. The vehicle must also launch into a target, not just upward. Here again, everyday intuition misleads us. Leaving a planet does not mean rising until you are in space, and then deciding what to do. If the crew needs to meet a return craft or departure stage in Mars orbit, the ascent has to deliver them to the right orbital region at the right time with the right velocity. Orbit is not a place you reach by height alone. It is a state of motion. A vehicle could rise beautifully and still be useless if it cannot match the required path. It has to guide, steer, stage if the design requires it, manage engine performance, protect the crew, and arrive with enough precision for the next link in the chain. That precision depends on things that sound ordinary until they are happening on another planet. Sensors must understand the vehicle's attitude and motion. Computers must execute the guidance. Engines must produce the expected thrust. Valve and lines must behave. Propellant must feed reliably. Structures must tolerate vibration and loads. Communication and tracking must support the operation, even if real-time human control from Earth is not practical in the familiar sense. The ascent is therefore not only a propulsion event, it is a trust event. The mission is trusting a vehicle that cannot be surrounded by Earth's launch culture. It is trusting pre-flight checks performed with far fewer hands. It is trusting stored or produced propellant. It is trusting that dust did not quietly defeat a mechanism. It is trusting the accuracy of software and sensors after a long wait. It is trusting that the crew can execute procedures while knowing that the rest of the return chain is above them, not beside them. And the surface itself complicates the psychology. On Earth, a launch has abort zones, support aircraft, tracking ranges, and a planet full of infrastructure. On Mars, the crew is leaving the only place where they currently have shelter. If the ascent vehicle has a problem before launch, they may still have the habitat. If it has a problem after launch, the situation changes quickly. The vehicle is no longer a future promise standing on the surface. It is the crew's only moving platform between a planet and an orbit. That is why lower gravity is not a satisfying answer. Lower gravity helps the rocket equation, but it does not provide a launch tower. It does not provide replacement technicians. It does not clean dust from every joint. It does not guarantee ignition after storage. It does not create orbital precision by itself. It does not turn a surface vehicle into an Earth return system. Mars makes launch cheaper in gravity, but more expensive in certainty. There is a useful contrast here. The outbound launch from Earth is massive, loud, and supported by enormous visible infrastructure. The Mars ascent may be smaller, quieter, and visually less grand. But it may be one of the most emotionally concentrated machines in the entire mission. Because if it fails to do its one job, the elegance of the return vehicle in orbit may not matter. The planetary window may not matter. The Earth entry system may not matter. The route home can exist on paper and in hardware and still be unreachable. This is the cruel logic of dependency chains. A later machine can be ready and still be useless if the crew cannot reach it. It also means that the ascent vehicle has to be understood as part of the surface plan, not an object that can be considered only on launch day. Where it sits, how it is checked, how the crew reaches it, how dust is managed around it, and how its state is reported all become return design questions. There is also the question of how much vehicle you dare to place on the surface. A larger ascent vehicle can carry more capability and margin, but it may be harder to deliver and support. A smaller vehicle may reduce delivered mass, but it can leave less room for comfort, redundancy, or late surprises. Engineers do not get to choose safe in the abstract. They choose balances. Mass against margin, simplicity against capability, pre-positioned confidence against surface complexity. Even the crew cabin is part of that balance. The ascent from Mars may not require a luxurious interior, but it must protect human beings during a high-consequence operation. Seats, suits, controls, displays, pressure systems, emergency procedures, and life support capacity all occupy mass and volume. The vehicle has to be small enough to be practical, but real enough to be a crewed spacecraft. It is not a drone with passengers added at the end. And because the ascent is one of the first active steps in leaving Mars, it carries a symbolic burden too. Until that engine starts and the vehicle commits to flight, the whole return system is still theoretical from the crew's point of view. The moment of ascent is when the promise of home changes from stored hardware into motion. A careful mission design does not simply hope the ascent vehicle works. It can build in monitoring, redundancy, robust storage, checkout procedures, protective placement, pre-positioning, automated health checks, and conservative margins. Engineers do not face this problem with theatrical optimism. They break it apart into requirements. They test. They simulate. They design for failures that can be handled. They try to remove mystery from the moment of ignition, but the central condition remains. The rocket home begins on Mars. It begins in a place without Earth's launch base underneath it. And as soon as you accept that, the next dependency appears. A rocket is only a promise if it has usable propellant. On Earth, propellant is produced, transported, loaded, inspected, and supported by an industrial chain. On Mars, every kilogram connected to the trip home has to be brought, protected, or made. So the ascent vehicle leads directly to the deeper question. If every kilogram is punishing, where does the fuel for coming home actually come from? In other words, launch begins long before ignition, while the vehicle is still silently waiting. That is why the ascent vehicle is less a parked rocket than a stored launch campaign. The simplest answer is also the most misleading one. Just bring the fuel. It sounds practical at first. If a crew needs propellant to leave Mars, then send the propellant with them, or send it ahead of them. Put enough in tanks, protect it, and make the return possible. That idea is not foolish. Pre-positioning supplies and return assets is a serious part of many broad Mars return concepts. But the phrase, just bring it, hides the mass multiplier that makes Mars return so severe. Every kilogram used later has a history. A kilogram sitting on Mars was once a kilogram that had to be launched from Earth, accelerated into space, sent toward Mars, slowed or delivered at Mars, protected during arrival, and placed where it could be used. If it is propellant, it may also need tanks, insulation, valves, plumbing, sensors, power, and a system that keeps it usable until the crew needs it. If it is part of a larger return chain, it may have required earlier cargo missions, landing systems, surface mobility, and verification. So a kilogram of return capability on Mars is not merely a kilogram. It is the visible tip of a long chain of mass, energy, and logistics. This is why the fuel problem can quietly dominate the whole architecture. A rocket needs propellant. More propellant means more tankage and structure. More tankage and structure means more delivered mass. More delivered mass means larger launch and landing systems earlier in the chain. Those larger systems may require more propellant of their own. The spiral does not continue forever in a cartoonish way, but the direction is real. Carrying the ability to come home can make the mission heavier before it ever begins. A human-scale analogy is packing supplies for a long expedition, then realizing you also need supplies to carry the supplies, protection for the carrying system, tools to maintain it, and spares for the tools. The pile grows not because anyone is being careless, but because dependency has weight. Mars return forces that lesson into hardware. One broad strategy is to send the return propellant or return vehicle ahead. That can reduce the risk of asking the crew to land if the homeward hardware is present. It also allows mission teams to verify, at least to some degree, that the return assets exist before committing humans to the surface. But sending large return assets ahead does not make them free. It moves mass and risk into earlier cargo missions. It asks those systems to land successfully, survive, and remain ready. Another broad strategy is to make some of the propellant on Mars. This is often discussed under the idea of using local resources. Mars has an atmosphere. It has surface materials. Depending on the architecture, some ingredients might be gathered locally, while others are brought from Earth. The exact chemistry and hardware choices can vary, and this script should not pretend that one pathway is universal. The important point is the architectural shift. The return mission begins to require a small industrial operation on another planet. That changes the story. A propellant plant is not a magic box labeled fuel. It needs power. It needs intakes, reactors or processing equipment, pumps, storage, thermal control, sensors, and verification. It needs time to operate. It needs to handle dust, cold, maintenance uncertainty, and imperfect conditions. It needs to produce not just something chemically interesting, but the right amount of usable propellant at the right quality, stored in a way the ascent vehicle can actually use. And if that plant is expected to work before the crew depends on it, then the mission has to ask uncomfortable questions. When does it start? How is it powered? How is performance confirmed? What happens if production is slower than planned? What if storage losses accumulate? What if a valve sticks, a filter clogs, a sensor drifts, a tank warms, a seal leaks, or a subsystem enters a state that Earth engineers can understand but not physically touch? These are not reasons to abandon the idea. They are the reason the idea is an engineering problem instead of a slogan. In fact, producing resources locally can be one of the most powerful ways to make a Mars mission more feasible. But the power of the strategy comes with a trade. You may reduce launched mass, but you add a requirement that Mars itself participates in the return chain. The planet must supply something useful. The machines must transform it. The storage system must preserve it. The crew must trust it. And the mission must know the difference between the plant ran and the return vehicle is ready. That last difference matters. A status light is not the same as confidence. A tank level is not the same as usable departure capability. A chemical process that works once is not the same as an operational system that can support human return. The fuel system has to be measured, validated, and connected to the rest of the return architecture. It has to survive not as a laboratory demonstration, but as a mission dependency. That is why this section must stay architecture neutral. The future may involve a combination of pre-positioned propellant, locally produced propellant, imported ingredients, surface power systems, long-duration storage, and conservative reserve strategies. The exact mix depends on mission design, but any credible mix has to face the same brutal question. How do you make the energy of coming home available on Mars without making the entire mission impossibly heavy before launch? Power may be the quietest part of this story. A production plant, storage system, and verification network all need energy over time. Solar arrays can be elegant, but they may be affected by dust, angle, season, and available daylight. Other power concepts may reduce some of those concerns while introducing their own mass, deployment, safety, and operational questions. The script does not need to choose the winning technology to show the pattern. Fuel is never only fuel. It drags power behind it. Verification is just as important as production. A mission cannot treat some propellant exists as the same thing as the ascent requirement is satisfied. The system must know quantity, quality, temperature, pressure, contamination, store loss data, transfer readiness, and connection to the vehicle. That means instruments. It means procedures. It means thresholds for deciding when humans are allowed to rely on the system. In a Mars return mission, confidence is engineered too. This is why fuel readiness would likely become one of the quiet psychological thresholds of a crewed Mars campaign. Before the crew thinks of the ascent vehicle as a way home, The mission must know that the vehicle is not merely present, but fed by a verified chain of energy and matter. There is also a quiet timing problem inside the fuel problem. If return propellant is made before crew arrival, then the mission needs confidence before the crew commits to landing. If it is made after crew arrival, then production becomes part of the crew's surface risk. If it is stored for a long time, then storage reliability becomes a return requirement. If it is brought from Earth, then delivery and landing become return requirements. Each answer moves the pressure, but none removes it. This is what engineering often looks like at the frontier. Not one dramatic obstacle, but a set of pressures that change shape when you press on them. Bring more fuel, and the launch mass grows. Make fuel locally, and the surface infrastructure grows. Store fuel longer, and reliability and thermal control become more important. Reduce reserves too much, and later stages lose margin. Add redundancy, and mass grows again. The problem is not that there is no solution. The problem is that every solution has to be paid for somewhere else in the system. A small production shortfall can also be more than a small number. If the ascent requirement was built around a certain usable reserve, then the missing portion may change launch timing, crew loading, abort options, or confidence in reaching orbit. Propellant margin is not an abstract comfort. It is room for uncertainty at the first active step home. When that room shrinks, the rest of the chain feels it. That is the part casual diagrams hide. They show a rocket lifting from Mars. They may show a tank beside it. They may show a clean arrow to orbit. What they do not easily show is the chain behind the tank. Power arrays or other power sources, chemical processing, storage behavior, health checks, spare parts, dust mitigation, automated operations, and the long verification process that turns propellant from a hope into a return capability. For the crew, the distinction is simple. If the fuel is there, usable and trusted, then the ascent vehicle is a path upward. If it is not, then the ascent vehicle is a sculpture of a rocket. This is why fuel becomes more than fuel. It becomes a stored decision about the whole mission. It decides how much mass leaves Earth. It decides what cargo must land before the crew. It decides how much surface power is needed. It decides how long machines must operate before people rely on them. It decides what kind of confidence mission control needs before allowing humans to descend to Mars at all. And it changes the meaning of home. Home is not just the blue planet in the sky. Home is the propellant plant that woke up before dawn. Home is the tank that kept its contents usable through cold nights. Home is the sensor that told the truth. Home is the valve that opened. Home is the reserve margin that was not consumed by a small surprise months earlier. On Mars, fuel is not cargo. Fuel is a promise the planet has to help keep. But even if that promise is kept, even if the ascent vehicle is healthy and the propellant is ready, the crew still cannot simply choose any morning, climb in, and leave. The planets are not waiting in a straight line. Earth and Mars are moving targets, and the route home opens and closes according to geometry. The next machine in the return chain is the calendar. That threshold shapes schedules, surface priorities, and the confidence to keep the return plan moving. It also decides how much risk the mission carries into the first minutes of departure. Now the story changes shape. So far, the return problem has looked like hardware: rockets, tanks, engines, power systems, propellant plants, storage, and vehicles waiting in the dust. But a Mars return is also controlled by something no engineer can bolt down. The planets move. Earth and Mars are not two stations fixed on opposite sides of a room. They are bodies orbiting the sun at different distances and different speeds. The distance between them changes. The direction from one to the other changes. The energy required to travel between them changes. A path that is reasonable at one time becomes wasteful, dangerous, or impractical at another. This is where the simple straight line map fails. On a poster, Mars may appear as a red circle and Earth as a blue circle, with a neat line between them. But an interplanetary transfer is more like entering traffic on a moving circular highway. You are not just aiming at where Earth is. You are aiming at where Earth will be after months of travel, while your own planet of departure has also moved on. That is why mission planners think in windows. A departure window is not a preference. It is not a convenient date chosen for a calendar. It is a period when the geometry and energy of the planets make a particular kind of transfer feasible. If the crew is not ready, or the vehicle is not ready, or the propellant is not ready, or a fault consumes too much time, the window can narrow or pass. And missing it does not mean waiting for the next bus in 10 minutes. On Mars, missing the bus can mean waiting for the planets to come back around. This is the midpoint refresh of the episode, because the return problem moves from machines into time. The mission is no longer asking only, can we build it? It is asking, can it be ready when the solar system allows it to be used? That changes every earlier dependency. The ascent vehicle has to be ready before the departure chain needs it. The propellant has to be ready before the ascent. The habitat has to support the crew through the waiting period. The crew's health, workload, spares, food, water, power, and mental endurance have to be designed around not just exploration goals, but planetary timing. The return vehicle or departure port capability has to be in the right place, with the right state when the moment arrives. A clock is now part of the machine. This is why the window belongs in the title promise. The brutality of returning from Mars is not only that a crew has to travel far, it is that they have to be ready when far away geometry becomes briefly favorable. A perfectly healthy crew at the wrong time is still trapped by energy. A perfectly fueled rocket after the window closes is still waiting for the sky to become useful again. This is hard for human intuition because the clock is huge and invisible. A person standing on Mars would experience ordinary seeming days, work routines, maintenance checks, science tasks, meals, sleep, alarms, and quiet hours. But above that routine, the planets are slowly arranging or misarranging the path home. The return window is not a door in the habitat wall. It is a shape in orbital geometry. Picture Earth and Mars as two clock hands moving around the sun. At some positions, the line between them makes a usable path. At others, it does not. The return is not delayed by indecision. It is constrained by motion. This also explains why a surface stay cannot be treated casually. A long surface stay may create opportunities for science, preparation, and alignment with a return window, but it demands supplies, reliability, radiation mitigation, dust management, power stability, medical planning, and maintenance over time. A shorter stay may reduce some surface exposure, but it may require different transfer energies or mission designs. Again, there is no free answer. Time is traded against mass, energy, risk, and human endurance. The important point is not to choose one exact mission calendar. The important point is to show that the calendar is not outside the engineering. It is one of the engineering constraints. Imagine a train that only comes when two moving cities happen to line up across an ocean. You can build the station. You can pack the luggage. You can repair the tracks. But if you are not ready when the geometry opens, the station becomes a waiting room. And on Mars, the waiting room itself consumes resource sources. That is why a missed window is not merely frustrating. It can expand the whole problem. More waiting means more life support use. More waiting means more chances for small equipment failures. More waiting means more exposure to the environment. More waiting means more crew fatigue. More waiting may mean more pressure on stored supplies and surface systems that were already sized with assumptions. A delay can spread backward through the architecture like a crack. Even a calm diagram should make this visible. The launch window is not a decorative label beside the orbit. It is the gate that turns stored hardware into an actual route. Before it opens, readiness is waiting. After it closes, readiness may no longer be enough. This is also why Mars return planning can feel counterintuitive. On Earth, a delay often suggests caution. Wait until the system is better. Wait until the weather improves. Wait until the next shipment arrives. On Mars, waiting can still be wise, but waiting also spends the mission. Supplies are consumed, hardware ages, human endurance is used. The crew may be safer delaying a risky ascent, yet less safe if the delay pushes them toward a worse window or a longer stay. Time is not neutral. The calendar also shapes what backup means. A backup plan cannot simply be a vague statement that the crew will leave later. Later may mean a different trajectory, a different amount of energy, a different life support demand, or a different risk profile. A credible backup has to fit the same moving solar system as the primary plan. Even contingency planning has an orbit. The return chain, therefore, has two kinds of gates. Some gates are physical. An engine must start, a docking mechanism must work, a tank must hold. Some gates are temporal. The planets must be arranged. The departure opportunity must be open. The crew and vehicle must be ready before that opportunity closes. The mission has to pass both. This is why the return from Mars can feel so calm and so severe at the same time. There is no villain in the story. The planets are not hostile. They are simply moving. The brutality comes from the fact that their motion does not care whether a valve is late. A filter needs replacement, or a crew procedure takes longer than expected. Engineering has to meet celestial timing. And once you see that, the next pressure becomes obvious. Waiting is not empty. Waiting is work. Waiting is consumption. Waiting is maintenance. Waiting is medical confidence. Waiting is the slow use of margin. The crew is not only waiting for equipment. They are waiting for the solar system to briefly become cooperative. That cooperation is temporary, mathematical, and indifferent to the hopes of anyone standing under the Martian sky. It is one of the few clocks no crew can reset from the surface, no matter how ready the hardware feels. If the planets set the departure clock, then the habitat and spacecraft have to keep human beings alive long enough for that clock to matter. That turns the return problem from a machine problem into a human system problem. The trip home from Mars is brutal because the passengers are not separate from the machine. They are inside the machine. They maintain it. They depend on it. They consume its supplies. They add heat, moisture, waste, stress, judgment, fatigue, skill, and vulnerability. And by the time the return begins, they are not at the beginning of a clean mission. They have already lived through launch from Earth, outbound transit, Mars arrival, surface operations, isolation, dust, maintenance, and the slow psychological weight of distance. So when we talk about the trip home, we are not only talking about engines and trajectories. We are talking about a living system that must stay balanced for a very long time. Start with air and water. In a short journey, you can imagine carrying supplies in a more direct way. But for a Mars-class mission, every consumable becomes a mass and reliability problem. Air has to be managed. Carbon dioxide has to be removed. Oxygen has to be supplied or regenerated. Water has to be stored, recycled, purified, monitored, and trusted. Waste has to be handled. Humidity has to be controlled. Filters, membranes, pampas sensors, tanks, seals, and software all become part of the return chain. A life support loop looks simple in a diagram. Air goes around, water goes around, waste is processed, useful material is recovered. But each arrow in that loop is a machine with failure modes. A clogged filter is not a philosophical problem. It is a schedule, maintenance, spare parts, and health problem. A sensor that drifts is not just a number on a display. It can change how the crew and ground teams interpret the state of the closed environment. This is why closed-loop life support is not just a comfort feature. It is a return requirement. The longer the mission, the more the system has to behave like a small, disciplined ecosystem. Not a natural ecosystem, but an engineered one, with boundaries and monitors and machines, doing the work that Earth usually does invisibly. On Earth, the atmosphere is vast. Water cycles through a planet. Waste disappears into large infrastructure. Medical care sits inside a civilization. On the way home from Mars, those planetary services have to be replaced by equipment small enough to launch and robust enough to trust. That is a hard exchange. The crew also needs power. Power for life support, communication, thermal control, computing tools, lighting, medical equipment, pumps, heaters, and possibly resource processing or transfer operations. Power systems do not exist as abstract capacity. They are hardware that can degrade, collect dust, suffer faults, or require maintenance. A return architecture has to keep asking, What still works after months or years, and what happens if the answer is slightly worse than planned? Then there is radiation. The script does not need to claim specific doses or outcomes to make the point. Beyond Earth's protective environment, crews face radiation risks that have to be managed through mission design, shielding, storm shelter concepts, timing, monitoring, and operational choices. Radiation is not a monster in the hallway, but it is a background constraint that accumulates. It turns duration into biology. The longer the crew remains exposed across surface operations and transit, the more carefully the architecture has to manage that exposure. There is dust too. Martian dust is not just a color in the landscape. It can become a mechanical and operational issue. Dust can cover surfaces, enter joints, contaminate suits, complicate seals, affect radiators or panels, and turn ordinary maintenance into a repeated ritual. Again, the point is not to exaggerate it into a horror story. The point is that small environmental frictions can matter when the mission depends on equipment staying trustworthy over time. And then there is repair. Repair sounds reassuring, and it is. Human crews are adaptable. They can diagnose, improvise within procedures, replace components, clean, inspect, route around problems, and make decisions that a fully automated system might not handle as gracefully. This is one of the reasons humans are powerful explorers. But repair is also a cost. It uses time, it uses tools. It uses spare parts, it uses attention, it may expose the crew to risk, it may consume consumables. It may create new configuration states that need to be tracked. A spare part carried for one system cannot also be mass allocated to something else. A tool that seems minor on Earth can become precious when there is no hardware store on Mars. This is where the human system problem becomes quietly severe. Every spare part is a bet about the future. Every redundancy adds mass. Every maintenance procedure adds training and workload. Every simplification may remove capability. Every extra capability may add complexity. The return mission is not just asking, can the crew survive? It is asking, can the crew, the habitat, the ascent vehicle, the return craft, and the support systems remain inside a stable envelope long enough for the return chain to complete? Medical autonomy belongs in the same frame. On Earth, medicine is surrounded by hospitals, specialists, imaging equipment, pharmacies, logistics, and other people. In deep space or on Mars, medical care must be planned around distance, communication delay, limited equipment, limited crew roles, and the impossibility of quick evacuation. A small condition that would be manageable on Earth may become a mission planning concern because the crew cannot simply step into the larger system of civilization. This does not mean every mission is doomed to medical crisis. It means the architecture has to respect the fact that human bodies are not replaceable components. They need sleep, nutrition, movement, treatment, psychological stability, privacy, teamwork, and meaningful routine. A calm schedule is not a luxury. It is part of keeping the return capability alive. Food belongs in the same quiet category. It is easy to reduce food to stored calories, but for a crew living inside a long mission, food is mass, packaging, nutrition, morale, storage stability, waste management, and routine. A meal is not just fuel for a body. It is one of the repeated signals that the mission is still orderly. The return architecture has to preserve that order even after the novelty is gone. Psychology also has to be treated carefully. The point is not to invent drama between crew members or turn isolation into entertainment. The point is simpler and more technical. People make better decisions when the environment supports rest, communication, meaningful work, privacy where possible, and confidence in the plan. A return mission needs human beings to remain not just alive, but capable. This is also why routine matters. A checklist completed without drama, a filter replaced on schedule, a medical measurement taken before it becomes urgent, and a repair logged clearly for the next shift are all small acts of return engineering. That is why a sleep-first narration should not turn this section into suffering imagery. The more accurate picture is quieter. A crew member checking a panel, a filter cartridge being replaced, Water moving through a loop, a storm shelter marked in a diagram, a spare parts wall with labels, a doctor on Earth sending guidance that arrives after delay, a routine that keeps the system from becoming dramatic. Real engineering often tries to make danger boring. That is the repair beat here. The problem is brutal, but not because astronauts are helpless. It is brutal because keeping people safe across such distance requires thousands of small protections to keep working. Redundancy, procedures, training, automation, medical planning, shielding, monitoring, and conservative design all exist to make the return survivable. They are not signs of fear. They are signs of respect for the chain. Still, none of them erase the accumulation. By the time the crew prepares to leave Mars, the mission is old. Not ancient, but used. Machines have run. Habitats have been lived in, filters have loaded, batteries have cycled, dust has settled, procedures have been revised, people have adapted, supplies have decreased. Every day may be normal, but normal days still spend margin. This is the human meaning of the return window. The planets may set the date, but the crew and systems must remain ready until that date arrives. A return mission is therefore not one machine waiting for one ignition. It is a living reliability chain. The crew has to be healthy enough to launch. The ascent vehicle has to be ready enough to carry them. The return craft has to be ready enough to receive them. The life support system has to continue through the coast home. The navigation and communication systems have to support the path. The Earth entry system has to remain protected for the final test. And all of this happens while Earth is too far away to become a repair shop. That is why the passengers are part of the system being protected, not as weak points in a dramatic sense, but as living requirements that the entire architecture exists to carry through time. The trip home is brutal because the people inside it cannot be treated as cargo. They are the reason the chain exists, and they are also one of the chain's most delicate continuous loads. And even if that living system endures, even if the ascent vehicle is ready, even if the fuel is usable, even if the planets have opened the window, Mars still demands one last act of precision before the long coast home can truly begin. The vehicle leaving the surface has to meet the rest of the return system in orbit. Again, quiet discipline matters. At this point, the story starts to compress. All the earlier problems are still present, but now they have to converge into motion. The ascent vehicle has to leave Mars. The orbit has to be right. The return craft or departure stage has to be reachable. The crew has to transfer, dock, or otherwise join the next part of the architecture. The departure burn has to send them onto an Earth-intercepting path. The crew's corrections have to refine that path, and the final arrival has to meet Earth's atmosphere correctly. This is where the return chain becomes narrow. Begin above Mars. A small vehicle rises from the surface and enters orbit. Somewhere nearby or in a planned orbital relationship, another element may be waiting. A return vehicle, a departure stage, a habitat for the trip back, or a system that contains the energy and life support for the next leg. The details can vary, and this script should not lock itself to one named architecture. But the operational logic is clear. If the ascent vehicle is not the whole Earth return ship, then leaving the surface is not enough. It must reach the next link. Rendezvous is one of those words that sounds gentle until you remember what it means in orbit. Two objects are not simply floating close together like boats on a pond. They are falling around Mars along paths defined by speed, altitude, timing, and direction. To meet, one vehicle must adjust its orbit relative to the other. It must approach with controlled motion. Sensors, navigation, communication, docking systems, procedures, and software all have to behave. The crew cannot simply steer like an aircraft toward a visible target. Orbital motion is more subtle than that. That is why space rendezvous is a known skill, but not a casual one. Human spaceflight has deep experience with orbital meeting, docking, and station operations near Earth. That knowledge matters. It means the problem is not magic, but Mars changes the support environment. Earth is far away. Communication is delayed. Real-time hand-holding from mission to control is limited. The vehicles may have been operating for a long time. The crew may be tired. The ascent has just occurred. The timing may be tied to a departure opportunity that cannot be treated as a flexible appointment. Known skill, harder setting. That phrase applies to much of Mars' return. Ascent, rendezvous, transfer, life support, re-entry, none are pure fantasy. The brutality comes from asking them to link across distance, time, and accumulated mission age. If the crew reaches the return vehicle, the next is commitment to the interplanetary path. A departure burn from Mars' vicinity is not just heading home. It is choosing a trajectory that will meet Earth later. The spacecraft leaves one moving planetary neighborhood and enters a solar orbit designed to intersect another moving planetary neighborhood months in the future. A tiny drawing can show this beautifully. Mars here, Earth there, a curved path between them. But the clean curve hides a chain of precision. The spacecraft must depart with the right energy. It must point correctly. It must use propulsion as planned. It must track its state. It must communicate enough for navigation support. It must perform course corrections. It must preserve life support, power, thermal control, and attitude control. It must keep the crew functional. It must arrive not at an idea of Earth, but at a very specific arrival condition. This is where the return begins to feel like threading a needle from another planet. Again, not because engineers are guessing. The mathematics of orbital transfer is mature. Navigation techniques are powerful. Spacecraft can be tracked with extraordinary care, but the mission has fewer casual options than a local journey. If a correction is missed, the later correction may cost more. If a system degrades, alternatives may shrink. If a consumable margin is consumed, the remaining choices become less comfortable. The closer home gets, the less the mission can afford to be vague. There is also communication delay. A returning spacecraft is never cut off from Earth in the romantic sense. Mission teams can support, analyze, plan, and advise. But they cannot make Mars and deep space behave like a room next door. Signals take time. Situations must be handled with autonomy, pre-planned procedures, onboard judgment, and robust systems. The crew and spacecraft have to be able to continue through ambiguity without waiting for instant rescue from the ground. That is another way the return chain becomes mature. Early in the mission, delays can sometimes be absorbed by planning. Late in the chain, delay interacts with shrinking margins. A system that was merely inconvenient in one phase can become central in another. The docking or transfer moment also reveals another hidden dependency: interfaces. Vehicles built for different phases must still understand each other physically and operationally. Hatches, ports, seals, pressure systems, electrical connections, communication protocols, suit procedures, and emergency modes all have to be compatible. In a simple diagram, two craft touch and the crew moves across. In a real architecture, that contact is the result of decisions made years earlier by teams who had to imagine this exact moment. After departure from Mars, navigation becomes a long act of attention. The spacecraft may appear to be coasting, but coasting is not the same as doing nothing. Its position is measured. Its trajectory is refined. Small burns may correct the path. Systems are monitored. The crew lives inside routines that keep a quiet line pointed toward Earth. The drama is low, but the precision is continuous. And near Earth, recovery is part of the system too. The mission is not complete at first contact with the atmosphere. The vehicle has to descend, slow, survive heating, reach the planned recovery mode, and be found and supported after landing or splashdown, depending on the design. Even the last minutes are connected to planning, made long before Mars disappeared behind the crew. Then comes Earth. Earth is the destination, but it is also the final physical filter. The atmosphere that protects the planet also punishes wrong arrival. A returning vehicle from deep space has to manage tremendous energy. It must enter within an allowable corridor. The heat shield must be ready. Guidance has to manage the path. Parachutes, lift, propulsion, flotation, landing systems, or recovery methods depend on the design, but the general truth remains. Arriving at Earth is not the same as being safely home. This is one of the strongest reversals in the episode. The atmosphere is the thing the crew is trying to reach because it allows the final slowing and recovery. But it is also the thing they must meet correctly. It is a door and a wall at the same time. Too casual a visual would show a capsule streaking into a beautiful blue planet and end there. A better visual shows a narrow glowing wedge around Earth, a corridor rather than a target. The spacecraft does not need to hit Earth in the broad, emotional sense. It needs to arrive through a set of conditions that turn deep space speed into survivable descent. By this point, every earlier section is present again. The ascent vehicle mattered because without it, the crew never reached orbit. The fuel system mattered because without usable propellant, the ascent never happened. The planetary window mattered because without geometry, the departure path became unacceptable. The life support systems mattered because the crew had to remain alive and capable through waiting and transit. The rendezvous mattered because surface ascent was not necessarily the same as Earth return. Navigation mattered because home is moving. Re-entry mattered because the final planet still demands precision. The closer the spacecraft gets to Earth, the more tempting it is to let the story soften into certainty. But physics does not soften because the planet is familiar. The final navigation, thermal, communication, and recovery requirements still have to be honored. At this late point, there is very little value in theatrical language. The real tension is cleaner than that. A spacecraft can be mostly healthy and still need exact navigation. A crew can be almost home and still need thermal protection. A mission can have succeeded for years and still require the final hour to obey physics. Mars return is severe because success does not become automatic as the story nears its end. This is the proof of convergence. The return from Mars is brutal, not because one step is impossibly dramatic, but because the steps are linked. The chain does not care which link feels least cinematic. A quiet tank valve can matter as much as a glowing rocket plume. A calendar window can matter as much as an engine. A crew checklist can matter as much as a trajectory. A heat shield stored and protected for years can matter as much as the first launch from Earth. And late in the mission, the emotional geometry flips. At launch from Earth, the crew is leaving home behind. On return from Mars, the crew is approaching home. But the path may be at its narrowest. Earth grows larger. The familiar planet fills more of the window. The word home becomes stronger. And yet the spacecraft must become more precise, not less. That is why the final approach is not just relief. It is the last demonstration that home was engineered into the mission from the beginning. The closer home gets, the less the mission can afford to be vague. A successful return is not a victory over physics. It is a long agreement with it, kept until the last gate opens. The return works only when the mission remains specific all the way to Earth. Even the welcome planet must be approached with exactness until the very end. So the final question is not simply whether Mars is far away. Distance is only the stage. The real question is what kind of system can create a homeward path from another planet and keep that path alive until the moment human beings need it. That is no longer just a rocket question. It is a civilization question answered through engineering. Return to the first image. The dust has settled. A habitat sits on the Martian surface. The ascent vehicle stands nearby. Earth is a small point in the sky. At the beginning, that image looked like a crew that had already reached the great objective. Mars was the destination. Earth was the place behind them. The hard part seemed to be the distance already crossed. Now the same image means something different. The point of light above the horizon is not simply where the crew came from. It is the final end of a chain that must already exist. The ascent vehicle is not background hardware. It is the first door. The propellant system is not a technical detail. It is stored confidence. The habitat is not only shelter. It is the system that keeps people alive while the planets decide when the next gate opens. The orbital path is not a line on a chart. It is a meeting that must be earned. The return craft is not a waiting room in space. It is the next dependency. Earth's atmosphere is not just welcome blue air. It is the last narrow corridor. The small point of Earth in the Martian sky is therefore not a sentimental detail. It is a measurement of responsibility. If humans choose to stand on Mars, they must also choose to make that point reachable again through machines, timing, discipline, and patience. The beauty is not that Mars becomes easy. The beauty is that the difficulty becomes legible. That is the reframe. A Mars mission is not 2 trips with a landing in the middle. It is one return architecture that begins long before the crew leaves Earth. The outbound journey is spectacular because it is visible. The launch is loud. The spacecraft is bright. The landing is dramatic. The first step on Mars would be historic in a way almost everyone can feel immediately. But the return is quieter. Much of it is hidden inside design choices made years earlier. It lives in mass margins, stored propellant, surface power, reliable valves, sealed loops, spare parts, orbital calculations, heat shield protection, crew training, and procedures that no one watching a simple animation would ever notice. That quietness makes it easy to underestimate. But quiet does not mean simple. The return is brutal because it has to be solved before it happens. It has to be included in the first launch mass, the cargo plan, the surface layout, the power budget, the life support design, the mission calendar, the crew workload, the orbital strategy, and the final arrival system. It is not a question that waits politely until the exploration is done. It is present from the beginning, asking every part of the mission to prove that home remains possible. And that is why the problem is not only frightening, it is clarifying. A brutal engineering problem is not the same as an impossible one. It is a problem that refuses vague thinking. It forces every assumption into hardware, every hope into a margin, every diagram into a sequence, every dramatic phrase into a testable link. It asks civilization to do something very difficult. Build a path away from Earth that still contains Earth at the end of it. That may be the deepest meaning of a crewed Mars return. Not the footprint, not the flag, not the headline that humans reached another planet. Those would be extraordinary, but they are not the full proof. The fuller proof is that humans can go to another world and bring the path home with them. Not as a feeling, but as a working system. That final idea changes the emotional center of the mission. A Mars return is not only an act of bravery by the crew, it is an act of memory by the whole system. The mission has to remember through hardware, software, procedures, supplies, and margins what the crew will need long after the first launch applause has faded. It has to remember on the surface. It has to remember in orbit. It has to remember during the quiet coast home. This makes the final image calmer, not weaker. The more clearly the chain is understood, the less it needs spectacle to feel immense. And when the chain finally works, the achievement is not that nothing difficult happened. The achievement is that difficulty was anticipated. The path home was not discovered at the end. It was preserved. So when we say the trip home from Mars, we should not picture a simple arrow reversing direction. We should picture the row of gates: surface survival, ascent, propellant, timing, human endurance, rendezvous, departure, cruise, Earth entry, recovery. Each gate is a promise made earlier. Each promise has to remain true longer than comfort wants it to. And by the time the crew needs the last gate, the mission has already spent years proving the earlier ones. That is why home, in this story, is not behind the astronauts. Home is not waiting passively in the sky. For a Mars crew, home is the system that still has to work. And if that sounds severe, it should. But it should also sound beautiful in the precise, quiet way engineering can be beautiful. Not because the machine is shiny, not because the danger is dramatic, but because a chain can be understood, strengthened, tested, protected, and finally trusted. The trip home from Mars is brutal because every link matters. And it is possible only if the meaning of home is built into the mission before anyone ever leaves Earth. That is the quiet awe at the center of the problem, and that is enough.